What software are you using?
Uh, oh, can you hear
Using a
me?
software? Yeah, I can hear you.
Oh, it's this. This is why. Can you hear me?
Yeah.
Yeah, this the thing's a bit loose. OBS.
Yeah, that's what I was using, yeah.
Yeah. So
But
it's
the problem with that I found was that I had to downgrade my audio.
you had to downgrade your audio.
Yeah, so I have a 32-bit. Oh, fucking hell, I have a 32-bit. Your video just started playing ads to me. I've got the video open. Uh, yeah, I have a 32-bit like recorder, and it's like no, you have to be 16-bit, and it has to be like 48 kilohertz. And I normally like use like much higher settings than that, so I had a big pain last time trying to get it down.
I see. Right. So the thing will start in a couple of minutes. Did you see the results I sent through? So it looks really nice actually. I just have to finish the integral
Yeah,
bit, but so it's about 25% higher as you get super close in, which is interesting. 20 to 25%, which is not insignificant.
the flux on the planet is 20% higher.
Yeah, 20% higher if you're like sat basically on top of it, and then goes between that and zero at about 20-25 planetary radii from the surface.
That is interesting, yeah. Because the sun shading works in the opposite direction.
Exactly,
Yes.
exactly. So you've got the two competing effects, right? I mean, as you know.
Yeah.
So you've got the higher flux from getting closer, and then you've got more shading as you get closer. So
Nice.
it starts to take off so quick with the higher. In fact, I could probably plot the two effects as well against one another and
Yeah.
see what they're made up of.
Right, because you could just count rays that hit within like the
Yeah,
normal day side part
as
of
if
the
it was just a flat. Yeah, exactly.
yeah, yeah,
And we can see from there, so it should be good.
yeah. You should try log scaling the x-axis as well, and like doing a grid in log because it looks like everything that's happening in that very narrow part of once you're close in, right? That's when everything's kicking off.
Yeah, I agree. I think you're right. Right, let's have a look at this now. So I'll get Soph to check that everything's working as well. Right, so let's transition into this. So we should be up and running now. So let me get up the first topic, and we will get into this if you're ready.
Let's do it.
So, what's up, you scholars of enlightenment? Welcome to a very special live Q&A today. For anyone who's wandered over from Dave's side, I'm Dr. Sam Gregson. I'm a high-energy particle physicist, formerly of the Large Hadron Collider and CERN and Cambridge University. And today we're going to be discussing and answering your questions about some very fascinating findings. So, the potential discovery of a chemical marker of biology in the atmosphere of Venus, the discovery of a Jupiter-sized planet around a white dwarf, and maybe even the physics Nobel Prize if we get time. In fact, we might start with that because it's very topical, came out today. So to help us unravel all those wonderful things, we welcome back friend of the channel, my friend and ace astronomer, Professor David Kipping of the Cool Worlds Lab at Columbia University. Dave, welcome back
Hey,
to the show.
I feel like I'm Ace Rimmer when you introduce me that.
What a guy. What a guy. Yes. So, Dave, what's new since you were with us last?
It's been a lot, man. It's been a busy couple of weeks in science, which has been great because the world needs a distraction right now from all the madness going on. So science has been busy. I mean, the Venus stuff obviously was, as we'll talk about, has been really dominating the news, and then we've had the Nobel Prize that we'll talk about, and in exoplanets, there's been tons of papers coming out. So, and my team's been really busy. So we've started the semester. So we've just started teaching here.
Yeah.
New students coming in. It's all go. It's like all engines firing right now.
Good. So busy, basically.
Always.
Always. Right. So maybe if we get into the first topic, which, bit of misadvertising for people. We said we're going to start with Venus. I think because of the timing, we're going to start with the Nobel Prize in Physics 2020 that was just given out today, actually. So it's gone to three physicists: Roger Penrose, Reinhard Genzel, I guess it's German Genzel, and Andrea Ghez. So this is an astronomical prize related to black holes. What's your take on this, and what have they got this prize for?
The prize is to do with black holes. So there was Roger Penrose. It's kind of split two ways. So Roger Penrose got the prize for his theoretical work.
Yeah.
On he's written many papers about black holes, but he's really demonstrated that this is a robust prediction. I mean, when you take Einstein's equations and you predict a black hole, it's pretty surprising, and people were skeptical about that. And Penrose's work really put the theoretical grounding to demonstrate these things really are a genuine outcome of relativity. And then the other half of the prize is going to the observational evidence of a giant black hole in the center of our galaxy, Sagittarius A star, as it's often called. And this object, obviously it's very hard to detect a black hole because by their very nature they're invisible. So they had a kind of a cool way of finding it. They were able to watch the motions of stars in the galactic center, and because they're orbiting so close to this hypothetical black hole, then you see them getting accelerated, like whizzing around a particle accelerator almost, due to the gravity of the black hole. So you see these very strange orbits, and from those orbits you can actually figure out that there's a black hole there and some of its properties and get a sense of what's going on. So it's kind of like an indirect way of detecting the black hole. We're hoping to eventually take a photo of the thing with the Event Horizon Telescope, which obviously we did for the Messier 52, I think it was, object. I think that was earlier this year. It seems so long ago now, but I think that was this year, 2020. We detected that object with actually got our first photo. And they're hoping to do the same thing for Sagittarius A star as well, which would be great. But we're pretty sure it's there irrespective of that. But I guess it's always nice to see a picture.
So to sort of underscore that, Penrose is getting it for the theoretical side of it. So Einstein, one of the implications of Einstein's work in general relativity was that we'd create these black holes, these essentially bounded areas in space. But even Einstein thought that these things couldn't possibly exist in reality. And Penrose came up with these mathematical models, these, I think they call them, is it bounded surfaces or constrained surfaces, that said that potentially these things could exist. And then we've got Genzel and Gez, who've been tracking these stars in the very center of our galaxy, seeing that they go around incredibly fast. I think looking at the science grounding of the Nobel Prize, they said that they've tracked the star S2 or SO2 that takes 16 years only to go round the center of the galaxy. So they've tracked that from start to finish, going round one cycle, and therefore it goes so fast that it must be a star that's very close to the center of the galaxy, and there must be something very compact in terms of size and also very massive, which is sweeping it around so quickly. Because at our position in one of the spiral arms, it takes us 200 million years to go round, which is, the dinosaurs were still walking around last time we got round one lap. So there's these stars whizzing around. So Penrose for the theoretical, and then Gez and Genzel for the best evidence so far we have that potentially there's a massive black hole at the center of our galaxy. Is that a fair summary?
Yeah, and these, by the way, the numbers are kind of ridiculous, because I was just looking this up before we chatted, but the stars which are whizzing around are moving at like over 10 million miles per hour around.
How much C? What's the fraction of C are they doing?
I don't know. I can't do that math. I can't go from miles per hour to C that quickly in my head.
That's why I thought throw it over.
I don't think they're moving at a point where you'd expect to see contraction or time dilation effects. The most dominant source of any kind of time dilation would just be, I think, because of your proximity to a giant black hole itself. Yeah. So you're orbiting in curved space-time. So that's most likely going to dominate your motion. Certainly that's true if you look at satellites that orbit around the Earth. And they do move pretty fast. They're moving like thousands of miles per hour, but it's nothing compared to C. Yet you get quite a significant time delay just from GR, from the time delay. And Penrose is also, in one of my favorite papers Penrose ever wrote was about this Penrose process, which, or the Penrose mechanism it's sometimes called. And it's an idea of how to extract energy out of a spinning black hole.
Oh, wow.
which is neat, right?
Sounds a bit like Halo. It sounds a bit like Halo Drive here. We're going into
very much. I mean, really, the Halo Drive, which I can explain in a few moments if you like, but in brief, it is one of many numerous ways that people have proposed since Penrose argued about this mechanism of extracting energy out of a black hole. People have come up with many, many different ways since then, but it was Penrose who really first figured that out, that it was possible to do it in any way.
Yeah.
And then people have been iterating on that idea since.
Cool.
Including me.
What I really like about this prize, and it feeds on from sort of the spirit of last year's prize, is the way that they've done the split between experimental and theoretical, because it shows really the falsifiability that's important in science. And as you sort of alleged or alluded to certain issues that are going on in the world at the moment, it tells us how important it is to be certain, to check, to go back and really make sure these things are nailed down. So you've got the theoretical side, Penrose saying, I think these things exist. And then we're looking at the best way of, or the best evidence we have so far of potentially proving that hypothesis. So it's got both sides of the scientific process in that. And I quite like that. And it's just like the prize last year where we had, was it James Peebles? Yeah, Peebles for his theoretical work on cosmology. And then Mayer and Kellogg for finding the first exoplanet. So it was, again, a movement from theoretical into experimental. I don't know how you feel about how they've gone in the last couple of years in that sense.
Well, I mean, that's pretty striking as well. And what's particularly striking is that over the last four Nobel Prizes in physics, 3 of them were awarded to astrophysics and astronomy. Now,
I was going to ask you a question about this.
Carry on. That's kind of interesting, right? Yeah. I wonder if the physicists are getting upset about this, because 3 out of 4. I mean, astronomy and astrophysics it's the oldest science. I'm in love with this science, but it is a subset of physics. So it's kind of interesting that the panel over the last 4 years have gone with astronomy. It tells me that what we're doing is the most exciting stuff.
So I was going to ask that. I've got to cut you off there as a particle physicist, someone who deals in the very small rather than very large. Because is this, and I mean this in the best faith possible, so don't take this in the wrong way, does the number of prizes that are going to astronomy at the moment tell us that we're in a sort of golden age of astronomy, new findings, new things are happening? Or is it that there's not much going on elsewhere, or that work that hasn't been recognised in the past, we now have a chance to catch up and recognise that with Peebles, with the work that's taken 16 years here to come about on the experimental side? Why have we got this pile up of astronomical prizes, do you think?
Honestly, I don't know. I mean, I definitely wouldn't say, there's nothing interesting going on anywhere else, but there's...
Well, I meant that in a relative sense, right?
Yeah.
Everything's relative.
These prize committees, I don't know how how do you choose the best physics discovery? There's so many. There's a lot of politics, let's be honest. There's a lot of politics involved in what goes behind this. And I mean, the panel have been criticized in the past for not having enough women laureates recognized. That's sort of been addressed here a little bit, because one third of the prize, or actually 1/4 of the prize to be correct, because half went to Penrose and the other half was split 2 ways. But one quarter of the prize this year has gone to a woman laureate. But there's a lot of politics behind this. I don't really understand how they make their decisions. Maybe
it's a very loaded term, isn't it? Saying your science is better than this science. It is a very, I mean, I guess it's how much really importance we infuse into it, rather than how important it actually is in reality. Obviously, £1 million or whatever you get is important, useful for your research, but I think we instill and imbue a lot of importance into it beyond the importance of the prize itself.
Right. It's probably a bit like being a presidential candidate or something, or a president even, that you'll make most of your money from the speaking fees you can afford to do afterwards, rather than the prize itself doing the job.
The Netflix, the Obama Netflix series and such. Yeah, you're probably right.
But these scientists are famously underpaid, so I don't know. It's necessarily a bad thing either. But anyway, I don't really have much insight into how the committee do this, but it's always controversial. Every year it's controversial. I don't really know what to say about it, except the fact it's good that astronomy keeps winning prizes. I'm happy about that.
Well, that's I think that's fair enough. And I think it is nice that this is. It feels like if we're going to go with the award ceremony analogies as well, it feels like a bit of a lifetime achievement award as well. You know, this is on the experimental side, a tracking of planets that's taken 16 years to do. You know, that's a hell of a dedication to the pursuit of science and a hell of a lot of work that's gone into that. And also, on Penrose's side is, a hell of a lot of papers, a hell of a lot of changes that he's brought forward and new ways of looking at things. So it feels like a lifetime achievement award as well, which I think is a nice sentiment, because it shows that a commitment, a dedication, a lifetime in science can also bear fruits, not just I was in the right place at the right time, and I found something and it's changed the world, because that's not really how day-to-day science tends to work, at least in my experience.
Yeah, and I have a kind of thought about this that will lead into our next topic, and that's what do you do when we detect life if we detect life on another planet? Who gets that Nobel Prize? Is it going to be is it a physics Nobel Prize, which because of the astronomy connection, or would it be a biology Nobel Prize or a chemistry Nobel Prize? You could make an argument for all of those, and it's going to be interesting because it's so rigorously delineated in terms of subject area, but increasingly science is becoming interdisciplinary, and I'm curious to see how these traditional prizes adapt to that.
Yeah, I agree. Right, that was a beautiful say. You see, this is why I like having you on the channel, because you know the showmanship of the thing, right? You know the showmanship of the thing. You know the ropes. Right?
It's not my first radio.
It's not it's not my first barbecue, sir. Right? So, beautiful segue into this finding of a potential chemical signature of biology in the clouds of Venus. So, how on Earth, or on Venus, could there be life on Venus? Because this is somewhere with a surface temperature of 460 degrees. It can melt lead, a pressure that's like being a kilometre under the ocean, incredibly toxic, carbon dioxide, sulfuric acid. The Soviet craft that went there I believe in the 70s, they lasted an hour before they sort of melted or short-circuited. How can we have life in this environment? It sounds absurd.
Right, it's extremely hostile on the surface, but that's really the key point, is that the surface could be hundreds of degrees Kelvin, but it doesn't mean that the clouds have to be the same temperature. And indeed, as you go up in altitude, the temperature drops. So as you get above sort of 50 kilometers or so up into the atmosphere, where the clouds are, you find the temperature and pressure are fairly similar to the conditions we enjoy here on the surface of the Earth. And so that's not new. People knew about that for a long time. And even Carl Sagan wrote about that and said that, there's a possibility of life living in the clouds of Venus. So we've known about this for a long time, but I guess it always felt somewhat speculative, to have life in clouds. After all, it's not what we're most familiar with. But on the other hand, over the years, we have started to see increasing evidence that life on Earth does live in clouds. It tends to settle back down. It doesn't just sort of hang out there and live and have its entire life cycle there. Kind of just due to its weight, it will eventually sink back down. And this is life which was wafted up, most likely from the surface. Now, if that's happening on Venus, it'd be very surprising that anything could survive in the clouds. Because if it goes down to the ground, that's bad. That's really bad news. That's a sterilization event, right? So you don't want that. But it is possible, because of the thicker atmosphere, that it's easier to stay buoyant. Potentially, life could be floating, hanging around in the clouds for quite kind of different to the life that we know. But that's why we're kind of excited about this possibility, and the evidence that was written about, what was it, like a week and a half ago or 2 weeks ago?
I had to pick you up on a tiny thing of this, and I promised Professor Sarah Seeger, who I chatted to about this, I would pick you up on a tiny thing in your video. So you said because it's easier to stay buoyant, but she actually sort of bristled at that slightly, because if you can see on the screen, she had to come up with this incredibly complex way of how these things can stay up. So the idea was that this life will hang out in droplets, water droplets in the clouds of Venus, and these droplets will smash into one another. Eventually, they become so large that they start to sag down. Potentially, as you said, a little bit slower because of the density of the atmosphere. And as they drop down, obviously things heat up. It's going to be an extinction event, as you said, but the water evaporates as you go down. So she suggested that what you get is essentially this haze layer of these desiccated, dried up bacteria, or simple microbes of whatever is in the clouds on Venus. And then updrafts then pick those things back up, throw them back into droplets, and the cycle goes round again. But it's very sort of contrived and hypothetical, because as you said, if these things drop down to the surface, you'd imagine that they're dead. So you have to have them stay up. So you have to imagine that they're sort of circling and in these sort of convective currents, 50, 60 kilometers above the surface, and they go into these dormant and alive and dormant and alive and dormant and alive states. It's a very it's very difficult to actually conjecture, and maybe we're being quite Earth-centric, but as to how these things could live in the clouds continuously, and there's a lot of things to sort of work out in that regard.
Right. I mean, then no one knows what the hell's going on, if there's even life there at all, let alone how that life could be floating around. So this, I agree, this is one mechanism that could work. I think you could think of others as well. And really, my only point was just that the fact the atmosphere is denser means it's easier to be buoyant, and that's it. It doesn't mean that you will be buoyant. It just means that it makes things a little bit easier. But how it is exactly staying up there, we don't know, and we don't even know if there is anything there, to be clear. We just have a hint of something being there. So I'm sure there's going to be lots and lots of interesting ideas about what this life could be like as time goes on. So
this begs the question, because if life can't go down to the surface, that suggests two things: either it evolved or abiogenicized, if that's the right word, in the clouds themselves, and then evolved in the clouds themselves, or it started on the surface and then migrated upwards. What is the best thoughts about how that might have happened? Because it seems strange to us, thinking that the life sort of evolved or began in situ in the clouds.
Yeah, I mean, it's a surprising place, certainly for abiogenesis to occur, because there's no real substrates apart from the water, the droplets perhaps. And normally you want to be on a substrate, and that just kind of concentrates the chemistry. So by a substrate, I mean like a 2D surface, rather than just, if we have just, random molecules floating around in a 3D volume, it's kind of hard to get them to come together to form complex chemistry. But when you have 2D substrates, it gets easier to concentrate things.
I guess like the surface of a catalyst would, it brings things into one place. Yeah,
exactly. So look, I'm not a biologist, so I have no idea which one of these is right, or how this really happened. But my best guess, since you're asking me, would be that it makes more sense that life adapted to this. It seems a fairly contrived setup for it to begin there. And in that sense, it's consistent with pictures of what Venus might have been like in the past. There was work done right here in New York by Anthony D'Argenio and I think it was Michael Way, who recently showed that Venus could have been persistent as Earth-like, essentially. Earth-like conditions, liquid water on the surface, temperatures not grossly indifferent to that of the Earth, for up to 3 billion years, and only perhaps recently went into the state we see in today, sort of 700 million years ago. So 3 billion years for life to get going, for evolution to get going. So if we assume life is there early on, then as it happened on Earth, then it would have had plenty of time to have adapted and had a chance to then, build the necessary internal machinery to cope with these conditions. And we don't know how sharp this transition was. If the transition was extremely sharp, almost like a meteorite impact, then it would have been very difficult for life to adapt. But if it happened over tens, millions, hundreds of millions of years even, then I think that makes a lot of sense that life could have adapted to those conditions.
So what was the actual finding? So the finding was a telescopic finding of a lack of light for the chemical phosphine? What was actually found and how?
Yeah, they used two ground-based telescopes here on the Earth to study the atmosphere of Venus. And by looking at the atmosphere, they could see, as you say, here's kind of the depiction. There's some missing light at the color of light, or to be more technical, the wavelength of light, where this particular molecule, phosphine, which is phosphorus with 3 hydrogens sticking off it, that molecule just likes to absorb light at that frequency. Yeah. And that's just because of the structure of the molecule itself. So it's like vibrational and rotational modes of the molecule. Now that's how we do it all the time. In astronomy, we've been doing that for donkey's years, looking for molecules all over the place in deep space, in interstellar medium, in the sun even. We've been doing this to detect atoms and molecules. What's I guess a little bit more challenging here is that there is only one line. Yeah. So every molecule doesn't just absorb one wavelength, they typically absorb a whole host of wavelengths that correspond to these different resonant frequencies to what the molecule sort of gets excited with, it just has the right wavelength to trigger these transitions. And so it's kind of a little bit sad that we don't have more evidence here. We just have this one single line. Yeah. And if we had lines detected in multiple wavelengths, I think many of us would feel that was a stronger detection. It's a little bit unusual actually in astronomy to claim a molecule just based off a single line. Yeah. However, the significance is quite strong. I mean, it's so strong you can see it by eye in this picture, right? This isn't like pushing things to the hairy edge of detectability. This looks quite promising. So that's nice. And then actually there was a paper that came out quite recently, just after this one came out, in fact, because September 27th this came out. And a team used let me get this right, the Pioneer Venus Large Probe Neutral Mass Spectrometer. So there was a mission that the Americans NASA sent to Venus in 1978. And it did actually descend through the atmosphere. It didn't land. They lost contact with it before it landed. It wasn't really designed to land. But on the way down, it was able to sample the atmosphere. So this is a mission from the late 70s. Someone's gone through that archival data of that mission, which is stuff recorded in microfilm. Remember, this isn't like digital information. And they've gone through that old data and they find evidence that supports phosphine in that data that nobody had noticed before. So that's it's a little preliminary. They just sort of threw this on archive. It hasn't been peer reviewed yet. I think they're going back to the original microfilm tapes and trying to go all the way back to the very beginning of the analysis and redo it. But the fact that you can see it in this independent data set is really nice. It means that there probably is phosphine in the atmosphere of Venus.
That's incredibly cool. And this was done with, I think it was ALMA and the JCMT, was it? ALMA being this one you mentioned in a video you did on this, a really good video, is the one that produces these beautiful images of these protoplanetary disks. So 2 telescopes that we use to do that in the sub-millimeter range, and phosphine absorbs in these ranges. It's a chemical we don't expect to see on Venus, because you'd expect the phosphorus to be combined with oxygen. You've got this phosphorus combined with hydrogen. And on the Earth, phosphine is obviously a molecule that's associated with life in swamps, life in abiotic environments. So seeing it there means potentially there's life. So if we've got this, I think it's a 15 sigma detection of phosphine, which when I went to the p-value table, it's not even on there. So it stopped at 8, and even as a particle physicist I stop after 5, 6. So in terms of statistical significance, they have found phosphine. Obviously it needs to be independently checked.
Well, they found the line of phosphine.
They found the line.
They found the line which corresponds to phosphine, but that's not quite the same as saying we found phosphine 100%. But
True. True. Yes, that is a good and a fair correction. So if we've got this high-level detection of phosphine, and we know on the Earth that phosphine is a chemical signature of life in certain environments, why can we not claim that we found life yet? And if not, what are the next steps to cleaning that up?
Yeah, so the big elephant in the room is what else can make phosphine
Yeah.
apart from life. So, I mean, even in the case of life, this is sort of associated with anaerobic bacteria that are thought to do this, and you see it in sewage and swamps. It's that kind of stuff.
Nice places.
It doesn't probably wouldn't smell too nice, but we don't really know how the bacteria is making it. The actual mechanism isn't fully understood, so it's not really clear if it's that life is directly using phosphine or producing phosphine, or that it produces something else, and then that something else then reacts to produce the phosphine. So it's like a knock-on effect rather than a direct effect. So don't really understand that too well. And then, of course, we don't really understand whether there are some abiotic processes, abiotic things other than life that could be producing it. So, for example, there is known evidence that ordinary iron with phosphorus containing impurities will react with sulfuric acid, which is in the clouds of Venus. If you have that combination, iron with phosphorus and sulfuric acid, that will actually make plenty of phosphine even at room temperature, which is basically the temperature of the clouds. So it's quite possible that an iron-rich meteorite material could be breaking up in the clouds, and then that's enriching the clouds with phosphine.
Yeah.
Eventually it would settle, but with enough supply, you could potentially produce phosphine this way. A second possibility is that it could be to do with volcanism on the planet. And again, actually, soon after that paper came out, there was, I wouldn't call it a rebuttal paper, but a paper which suggests this abiotic explanation and suggests that there could be active volcanism present on the surface, and phosphides could be brought up, which is basically like the phosphorus ion is essentially what it is. So it's just like add 3 electrons on to phosphorus, and you've got phosphide materials, and they could be brought up and then produce phosphine in subsequent reactions. So it's on Earth we certainly do know that phosphorus comes up from underneath the ground during volcanism. It's a little bit more volcanism than I think most people expected Venus to be having, but it is plausible that we don't really know much about the surface. As we said, like, it's covered in clouds. It's very difficult to really tell what's going on down there. So two possibilities are meteorites and volcanoes straight off the bat. But life remains a very exciting possibility as well. I don't want to turn that down either. So this is still doesn't dishearten me too much. I'm still very excited by this result.
So the big problem is that it essentially could be something else. We haven't closed off all pathways. I guess it's interesting though, isn't it? Because even if it is something else, it's new chemistry or a new finding, even because it's something that was unexpected. So even if it's not life, it is new complex chemistry. It is a new finding. So in that sense, it's still interesting and deserves a decent amount of fanfare. So if we've got this situation where we're essentially making inferences, we're trying to close off possibilities, isn't this all winding up to the idea that eventually we're going to have to go to Venus, drop something into the clouds, collect a sample, and do the in situ analysis?
I hope so. That'd be fun. I want to see a balloon or an airplane fly through Venus. I mean,
So what is the lead up to this? Because I had a quick chat with Sarah Seeger about this. She mentioned the Rocket Lab mission that's going soon, but it's quite small. It might be able to verify the existence of phosphine, but probably not do the detection. Then you've got these NASA missions, these discovery level missions, 4 of which are in competition at the moment. I think 2 of them survive. One of them is a Venus mission. So I think I can bring that up on the NASA website. So you've got this, Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, which is a bit of a mouthful. But potentially going to Venus, but more on the sort of structural side, but maybe could have things added to it to look at this possibility. What sort of timeframes, what sort of possibilities do we have for doing that?
Yeah, I mean, these ideas they've kind of existed for a while. People have been interested in sending missions to Venus for decades, and many people complain that Mars has had too much attention. The people who study Venus, I mean, if you go to a planetary science conference, there's tens and tens of sessions about Mars, and like there's some back room talking about Venus. That's how it's kind of been in the past. And I think,
is that because we're so Earth-centric and Mars is more like Earth? What's the reasoning there?
I guess the reason is because Mars is cooler. We certainly know there's ice caps on Mars, so we know there's H2O. And Mars is still very interesting. Don't get me wrong. It could have been. We see evidence, direct evidence, really. I'd say that there was water on Mars, both in the past and still today, in the form of this kind of briny liquid. So it's where there's water, there's a possibility for life. And NASA's policy really has been follow the water when it comes to life. Yeah. And so that's why Venus was ignored, because it basically doesn't have any water. It lost all of its water a long time ago, almost all of it. So for that reason, Venus has been ignored. And of course, the fact it's such a difficult condition to work in, as you said, like the Veneer landers lasted like an hour or something on the surface. So the temperature and pressure is just so extreme that it's like being on the bottom of the Mariana Trench, like the amount of pressure these things have to deal with. So I'm not surprised that it hasn't been a priority, but I'm hoping we're flying this mission called Dragonfly that's been selected, for instance, to go to Titan, which is actually going to be like a drone that will fly through the atmosphere of Titan and image all the lakes, the methane and ethane lakes on the surface. So there is now a mission selected that plans to fly on another planet, and Venus is another obvious place to attempt to do that. So I think as technology's matured, we're getting a bit more comfortable with the idea of doing that, and a balloon or some kind of glider in Venus's atmosphere, I think there's a lot of excitement about that now. I don't know the timeline though, to be honest with you, but I think it's sort of up to NASA, really.
You say glider. I don't know if you've seen, I'll put it up on the screen for you, this Breeze mission. Which is, if I just whiz this forward a little bit, is this sort of manta ray type thing that they want to flat through the atmosphere of Venus, and apparently it'll get a lift just like a manta ray does, sort of every couple of weeks. 4 to 6 days.
I hope they have cameras of each other. I want to see, I want to see this guy filming the other guy. That'd be such an epic shot.
Exactly, that would be awesome. But there's some really fancy designs being mooted. I think the difficulty that people are having at the moment is there was such fanfare about this potentially being live, but obviously to go and do the in situ check takes such a long lead up time in terms of time getting these things ready, in terms of money, and a lot of the things that are already on the slate, these discovery level missions, for example, they already have their own goals and their own technology that they want to go with, and their own instruments that they want to take, that you'd have to do some sort of hack job to do the measurements that they want for phosphine. So I think people are getting a little bit excited that this is going to be solved quite soon, and it's probably going to be,
I think you're looking at a decade.
The thick end of a decade.
Yeah. I can see one of your questions asks about terraforming Venus. I think it's just such a difficult thing to imagine doing. The atmosphere is 96% carbon dioxide. So, we're struggling with carbon dioxide levels here on Earth of 400 parts per million. Yeah. And we'd like to bring that down to like 350. So just to pull out 50 parts per million CO2 out the atmosphere. And you've got people spending billions of dollars trying to figure out new technology to do negative emissions, like geoengineering.
Storage.
Exactly.
Sort of thing, yeah.
And none of it's really at the point where we can seriously, reduce the atmospheric content. So to take an atmosphere that's 96% carbon dioxide and is a much heavier atmosphere, it's way denser than our atmosphere, and remove all of that CO2, that's basically what you're looking at. You'd have to pretty much remove all the CO2 to make it habitable. Yeah. Is mind-bogglingly difficult.
Well, before you start with the sulfuric acid that's flying around.
Yeah, there's a lot of problems. And then just working in that environment would be extremely difficult. So it would be abhorrently expensive to imagine trying to... Mars is a far easier, or the moon, just build bases on the moon. In domes and things would be far, far easier. So in the near future, I think that's the most likely. It's not exactly terraforming, but it's a way that we could live on these planets.
But I think that's an excellent question, by the way, Yash, and thank you for bringing that up there, Dave, out of the chat. But I think what Yash has done, either consciously or not, or unconsciously, has pushed on that idea that we do have this slightly Earth-centric, obviously, because we have one idea of how life started on the Earth, that going to Mars, we could live on Mars. There's potentially water on Mars. It's more like the Earth. And maybe that's why Venus has been slightly underserved recently in terms of that look for life.
Yeah, I mean, after the Apollo era, people were expecting to live on the moon and build bases on the moon.
Yeah.
And the next obvious step was to put a man on or a woman on Mars as well, and to eventually then colonize Mars. And that's certainly, in Elon Musk's vision of space exploration, is Mars is the obvious target for humanity's future. So it's easier. It's definitely easier on Mars to imagine people living there. But an obvious advantage to give Venus some fair play is that it really is the same size and mass as the Earth. And so gravity would be pretty much identical to that which we experience here. Mars will have reduced gravity. I think it's like 30-40%, something like this. So it's probably okay on the human body, but humans would be different if they grew up in gravity that was lower. You'd expect taller, thinner, lankier people like you see in this The Expanse show. You have this almost distinct human species eventually branching off because of the environments they live in. So that's the attraction of Venus, but there's so many things against it. I can't imagine until we're basically a Kardashev type 1 civilization being able to think about colonizing Venus.
You've beautifully pushed at a segue of our final topic as well, which is
that was unintentional.
Yeah, was it unintentional? But you see, again, the showmanship, good, about finding these Jupiter-sized planets around a white dwarf. Before we jump into that, I really want to touch, because it's a silly thing, but I love Jurassic Park, and last week I think this was based on Venus, although you can tell me otherwise. But I can't leave this alone because I love Jurassic Park and I've got this encyclopedic knowledge of these clips. So you posted on Twitter, controversial opinion, but life finds a way, which is the quote from Ian Malcolm in Jurassic Park. So I'll play it for the people who are not too sure what we're talking about.
It's not possible. Listen, if there's one thing the history of evolution has taught us, it's that life will not be contained. Life breaks free, it expands to new territories.
That beautiful man.
Barriers painfully, maybe even dangerously, but there it is.
You're implying that a group composed entirely of female animals will breed?
No, I'm simply saying that life finds a way.
So, life finds a way. And Dave, you see, you were pushing at that. You said a beautiful man. He is a beautiful man. I think you covered this because he's got the same luxurious black hair that you do. I mean, this is why.
That's why.
Yeah, you need the leather jacket. The leather jacket has to come, right? And the turning into a human fly. But that's later, right? Have you seen The Fly?
I have.
It gave me horrible nightmares.
I saw it when I was like 10 years old.
Yeah, so did I. And I was like, I never want to see this again. This like sicking onto his hand and it all melting away. I was like, God, please never let me see that again. Anyway, so you said controversial opinion, life finds a way. The Jurassic Park quote is a reference to evolution by natural selection and not the spontaneous emergence of life, abiogenesis, so the starting of life. We know a lot about evolution. We know almost nothing about abiogenesis. So is it fair to ask, you don't have to name names, but who was saying it was about abiogenesis? Because at the start of this clip, he seems to say it was definitely about evolution. And the context of this is that he's talking about the dinosaurs changing from one sex to another to be able to breed. So it seems to be obviously about adaptation, if not about evolution.
Yeah, I agree that he clearly isn't talking about abiogenesis. And whether it's adaptation or evolution, they're both sort of related to each other. But yeah, I take the film does some interesting things that are perhaps not the most scientific things as well. But anyway, let's. This is the thing. Like, I can't just now send a tweet without having to like justify what the hell I'm doing. It used to be that no one cared anything I said, and I could just say whatever I want. And yeah, now I have to like back up everything I said, put out there. No, but having said that, there was some reasoning. It was just because, I have made some videos on my channel where we sort of have played with the idea that perhaps life is a rare phenomenon rather than a common phenomenon, which is the typical popular opinion that you hear a lot of physicists and astronomers describe. So I did a video a while back pushing back against that, and I always get comments, by people that either fantastically love it, and they often come from the religious angle, or people that absolutely despise it and think it's incredibly what's the point of the universe if there's no other life, like that kind of perspective. And sometimes, not everybody, but sometimes you see the comment, life finds a way, put in the comment section. So it was really just that. It was really just me reading comments, which is always a bad idea, I guess, and then just throwing that out there, and I wasn't expecting to have to defend it too much. But
I can understand why people. It's an iconic statement from an iconic film. I can understand why people use it for abiogenesis. I don't have any problem with them using sort of that statement as a reasonable thing, I guess, even though we don't have really any experimental evidence of finding life on other planets. But I can understand why they use it. I think it's quite clear in this context that he's talking about adaptation and therefore evolution. Although I did catch myself, because in this he's saying that the dinosaurs will change from male to female in a single generation. So it's not actually evolution, it's adaptation within one generation. But then somebody else...
It's evolution, but it's not by natural selection.
Yes, correct, exactly. But then somebody jumped in and dug me out of my own hole, because then they said, well, in the film they're saying that they switch because of the frog DNA, and the frog DNA must have evolved to be able to switch between male and female. So it's evolution by natural selection by the back door.
Jurassic Park scholar.
Yeah. And at this point, we're digging far too deep into the science of Jurassic Park. But I thought it was just a little fun one that you dug up.
I know you want to move on, but I just say one other quote that maybe I shouldn't tweet about it then because of this reaction. But
go on, because I'm going to rip you up and down if it's bad.
This could be the test audience. In Contact, there's a quote that if someone says, well, what if we're the only ones out in the universe? And the main character says, Jodie Foster says...
Contact the one where they drop the ball through the spinning... Yeah. And it's 20 hours of static or whatever at the end.
I love the film.
It's a good film.
I love I really do, and I love the book, the original book by Sagan. But the quote at the end does bother me, because she says, well, it's an awful lot of waste of space if there's no one else out there, don't you think? And that, to me, that seems like a very egocentric
It's a value judgment about the rest of the space, isn't it?
Right, you're saying that like planets are a waste of time if there's nothing alive on it, or, I mean, not directly, but there's sort of an insinuation there that unless something is living, it is a waste of space. And as an astronomer, that kind of bugs me, because it's like, well, is a galaxy a waste of space just because no one's living there? That's maybe the universe just isn't designed for us. We're just here by chance. There's nothing wrong with that. So we do tend to get caught up in the idea that we are somehow like the pinnacle or the inevitable outcome of all of these processes, and therefore we'd expect it maybe to be happening elsewhere. But I
guess we see that over the history of astronomy, right, going from heliocentrism all the way down through Copernicus and the persecution of Copernicus and people like that there's a yearning within us to want to be the center of the universe and to be the main event, and that probably hangs on nowadays in more subconscious ways than it does in overtly religious ways, potentially.
Right. That's really well put. I like that phrasing, the main event. Yeah, that's exactly it. Yeah.
So it's like a boxing promoter. Good. Yes. Excellent. So maybe we should do an entire stream one day about our problems with the science in films, or quotes from scientific films. But we'll park that for another day, because you did a nice segue before we got into that section, and I cut straight across it, which was the final topic I wanted to talk about with you quickly, which is the discovery. I'll just get the new link up, actually. The discovery of a giant planet, Jupiter-like planet, or planet candidate at least, transiting a white dwarf. So we have this seemingly bizarre situation where we have a huge planet about the size of Jupiter and about 14 times the mass, they think, spotted around a tiny white dwarf star 80 light years away. So this is I think it has a really sexy name, WD 1856 is the star, and WD 1856 plus 534 is the name of the planet. So slightly confusing, not particularly sexy, but you have this bizarre situation where you would usually, center any picture of a solar system on the star, but in this case, they'd think you'd centered it wrongly on the planet, and it was the sun that was, obviously they're going around a common center of gravity, but it's bizarre that the star is smaller than the planet.
Yeah, in a sense that's expected though for white dwarfs. White dwarfs are, the end state of sun-like stars. Our sun will eventually become a white dwarf. It won't form a black hole or a neutron star. It's not massive enough to do that. So instead, the white dwarf essentially represents the core of the sun or a sun-like star, I should say, that isn't fusing anymore. It's just the leftover material. And because there's no fusion, then gravity sort of takes over and it just sort of shrinks right down until the point where degeneracy pressure, which is to say the actual resistive force between the electrons and the atomic nuclei, stop further collapse. So that's why it doesn't form a black hole, because the pressure isn't high enough to overcome those forces. So you end up with this dead, hot ball, and they're very small. They're like the size of the Earth, typically. I think this one's a little bit larger. And they just cool down over time. So it takes billions of years for them to cool down, but eventually they'll become what we'd call a black dwarf. And then the universe isn't old enough for there to be black dwarfs yet, but eventually they will form black dwarfs, just dead, inanimate object. Yeah. And, if these stars once had planets, so this is going to happen to the sun, remember, then it's not unreasonable that some of those planets might survive. Now, the inner planets probably not, because as the star evolves, you might know this, that the sun will become a giant star in its future. It will engulf probably even the Earth in the future, about 5-6 billion years time. And then after that, the outer planets will be disturbed in their orbits because of all the commotion happening on the inside. And so some of them might get ejected into deep space. Some of them might survive, and Jupiter is the most likely to survive just because it's the heaviest. It's the hardest to get out because it just has so much mass. And so this is a planet that's similar to Jupiter. And so perhaps we are looking at, in a way, Jupiter's future. This could really be where Jupiter ends up. It has to then spiral in. So this could happen. It could get kicked into an eccentric orbit through the gravitational interaction. Saturn's the most likely to do it. So Saturn's pretty close. If these two guys, their orbits move, so they get into a resonance with each other, that can excite Jupiter's orbit. Jupiter can get kicked into an elliptical orbit, and then it will circularize on the point of closest approach, which could be very, very close in to the star, in fact, in this case. And then you end up with a Jupiter around a white dwarf. So that's one possible, we don't really know how this thing got there, but that's one possible explanation.
So the reason people are excited about it, or it's got a lot of fanfare, is because we'd have expected, if it developed at the position that it is, that when the star became a red giant, it would have fried or kicked it out. It shouldn't be there. Is that why this is so exciting?
It can't have been living in that orbit when the star was a main sequence star, because it would have actually been inside the star itself. It's so close. So there's no way it could possibly have always lived there. There's definitely, this is unambiguously evidence for either migration in a system, or I said unambiguously, but then it's ambiguous. The other possibility is that it actually formed in a second generation. I think that's a little bit difficult to imagine, though, just because this planet's so massive. It's hard to imagine there was enough material. But once the sun goes into this giant phase, it kind of sheds these shells of material, and that forms what's known as a planetary nebula. So some of the most beautiful things you can look at through a telescope are called planetary nebula. They're really nothing to do with planets. They're just the shells of the star being flung off. It's just a complete misnomer that, we called it that, and then we were stuck with that stupid name for whatever reason. But the planet connection could be that those shells and the material that's left over could then go on to form new planets. So this planet could be very, very young. It could have actually only recently formed in the history of this entire solar system. It could have just formed once the star died. But I have to say, that seems to me a little bit contrived, just because the amount of material that's typically found around white dwarfs, it's difficult to imagine there'd be enough to form a super Jupiter.
Yeah. So what would be the implications of this finding? Is the idea here, so if we have this cool intact planet that's very close to the star, could this be a harbor for life? And essentially, could you have these, I guess, solar systems that people thought were dead solar systems after they've gone red giant and turned into white dwarfs now become more locations where life could exist?
Possibly. So, I mean, in this case, probably not because it's a giant planet. But look, the reason why many of us are so fascinated by these types of stars are that if they have Earth-sized planets around them, then the planet is pretty much the same size as the star. So that means that when the planet passes over the star, it blocks out some of the starlight, as happened here. It blocks out a huge amount of the star's light, potentially all of it, in fact.
Yeah.
And so you get these very, very deep eclipses. And because the way that we are currently looking, coming back to Venus even, the way we look for the atmospheres of planets, including exoplanets, is basically to study these eclipses when it comes to exoplanets. That's how we do it. And we look to see if the eclipses change in depth at different colors, and if they do, that tells us there's a molecule in the atmosphere that likes to absorb light.
Yeah.
And so just because these stars are so small, that boosts up the signal from, I mean, for the Earth around the sun, it's 80 parts per million. So that's 0.00008.
Yeah.
That's how much it dips. Here, it's basically completely disappears.
Yeah.
So that gives you the opportunity to really precisely measure the atmosphere. You could detect biosignatures almost on the cheap compared to, you wouldn't have to build like a giant telescope. You could use these small stars as a cheat code to achieve the same thing. So that's why we're excited about them. But you're right that this isn't the obvious place to look for life, because this is a dead star after all. It's cooling down. It's difficult to imagine a civilization living on these things because the stars are just transient. They're not sustaining a constant energy output even. They're just cooling down over time. But it is possible life gets going on these things, and it would be incredibly exciting if we could find some Earths where the temperature is currently right for life. And then I think it would be the sort of target that we would be throwing a lot of telescope time at to try and detect these signatures.
Cool. Also interesting from the point of view of the thing we've been discussing offline that I won't go into.
Yeah, that's right. And these things are so small. You can't just detect Jupiters or Earths. You can detect something the size of the UK passing over the star.
Yeah.
So you can detect like outrageously small things, like small asteroids, even passing over these objects. So small moons, things like this. So the potential to probe these systems is very deep compared to your typical star.
It's interesting what you say as well, because this could be, it's very speculative, but could be a view into the far future. So in 6 billion years, our sun is going to go through this red giant stage, or roughly 6 billion years, and probably consume the Earth, as you said. Maybe not Mars, but then these larger planets could be knocked into these closer orbits. So potentially a look into the future of our solar system. I guess
an eerie look into a dark mirror. It is kind of scary to look at these things in a way, but that's why I love astronomy. Is that astronomy really does give us the opportunity to look through time. Like both literally, when you look far away, you're looking through time because of the finite speed of light. But you're also seeing stars at different stages in their life cycle and their evolution, and that gives you opportunities to see how did stars form. We know how the sun formed because we can see stars just the same mass as the sun in the process of forming right now. Yeah. How do stars die? Like this is it. This is the end point. You can see it. So this is why astronomy is kind of special, because it's like a time machine. You get to really see things, the full scope of the life cycle.
Maybe we really do have to get to Mars to survive then.
Maybe that's the future. Yeah.
The future is basically Total Recall. So
perhaps recast. But.
There you go, with the 3 boobed women and everything. Yeah, definitely recast. Good. So, Dave, that was amazing. Thank you for going through all those topics with us. There's just a couple of questions in the chat, if you don't mind taking 5 minutes
to
sort of address those.
Take them quick.
So I got a question from Matthias Pizzini. How long does it take to build a spacecraft and take samples back if we started today? So I guess this is in in reference to Venus?
Just to build it doesn't take too long. You're probably looking at 6 months to a year of the actual construction, but you have to find the funding, you have to find the contractors to build it. You have to then test what you've built in the lab, make sure it's not going to break. So all of those parts take a lot longer. You can always cut corners. If you're a billionaire who is willing to fund it yourself and isn't interested in testing it, you're just going to throw it out there first time, then it could be very, very quick. It could be
calling Elon.
Right. So it's kind of a matter of risk. The more risk you want to take, the quicker you can do it. But you're looking at anywhere from a year at the fastest time scale to typically, like, we're looking at 10 years for the cycle of getting a new telescope launched.
Yeah, and if we got all the, as you say, if we go into the sort of public sector, there's always discussions around where money should go and the value and stuff, and the politics starts getting involved, which slows things down. So
yeah,
we're probably looking at if we're going to go that route, the thick end of a decade, as you sort of mentioned earlier. One more question in here from Yash. Just one more. How about experimentally terraforming a place on Earth, like the Atacama or any other extremely harsh place? I guess human beings have tried to do this in certain places with irrigation and such on a small level.
Right.
So it depends how terraformed you want it to be.
Yeah, and of course if you really try to take somewhere like Antarctica, so let's take Antarctica and make it completely habitable.
Yeah.
How would you do that? We'd have to warm it up. So
what does habitable mean, though? Are we being sort of UK, American,
right?
Temperate
if you want to do
zone?
farming and agriculture,
Right.
let's say, so we can
Okay.
have our way of life, then there's a couple of ways you could do that. You could increase the rate of climate change just so you can make Antarctica habitable at the expense of everywhere else.
So Yash, turn your lights back on. Just leave them
Or
on.
you could just nuke it. You could just drop a ton of nukes and then, or bombs that aren't necessarily. I guess the radioactivity might be a problem with nukes, but you just need to drop a lot of energy to melt all the ice. So you can think about ways of doing that.
Venus,
But
basically, and we're good to go.
yeah, it's not necessarily the most environmentally friendly proposal. I mean, I think a lot of us want to protect the Earth, and it's okay that there are uninhabitable regions on the Earth because that's kind of beautiful. When you go to the Death Valley, I kind of like having those habitable regions. So we could imagine doing those types of experiments, but I'm not sure it's that wise for us to be experimenting with our own planet too much because we actually live here and there's no turning time back if we mess it up. So we have to be careful.
And I guess the sort of simple terraforming that I don't know if we're suggesting doing this, but when we get to Mars, presumably you're going to want to see if you can grow things in the soil there. And I know there have been experiments in that regard as to whether it's feasible to grow certain plants in the Martian soil, which I think have worked in some cases and haven't in other cases.
Yeah.
So I guess we will want to do that on a small scale when we do these Martian missions. I think that's all the questions in the chat. Dave, again, I don't want to keep you for too long because I know you've got a lot to do.
Well, I do have to run, yeah, but it's been great having me on as usual, Sam, and thanks for the questions, guys, and I hope you guys enjoyed it. It was fun.
Yes, thank you very much. Dave's got to run, so anyway, you want to point people to Dave just before you get off?
Oh, you can just check out my channel, Cool Worlds, on YouTube. You just Google it, you'll find it, and we have a bunch of videos up there, so enjoy.
I like that you have to run just as the police symbol's going.
Exactly. They're coming.
Well.
I have to get out of it.
All right, Dave, I'll let you go. Thank you so much. Thank you for everyone in the chat. Thank you for the questions, and see you next time. See you later, Dave.
Bye.
Bye, buddy.